One of the fundamental topics in the study of the Earth is minerals. I bet you could name a dozen ways we use or places we find minerals. They're all around us. They make up the rocks that form mountains. When it rains or the snow melts or the waves of the ocean crash upon the shore, minerals get dissolved in and transported by water. The water we drink tastes differently depending on what minerals it contains. That's why natural spring water tastes different from purified water, which undergoes intensive filtering. Minerals are gemstones or other crystals such as the garnet and amethyst quartz seen here. Minerals also occur in many places we don't often think about. Minerals replace the organic matter of ancient organisms, preserving their shape as fossils. And what about minerals from space? The picture on the left is of a meteorite. The one on the right is astronaut Alan L. Bean, lunar module pilot for the Apollo 12 lunar landing mission. Astronaut Charles Pete Conrad Jr. is seen reflected in the helmet visor. They are taking samples of lunar soil for study back here on Earth. Now the Mars rover can analyze samples on its own, giving us the data without waiting for samples to get to Earth. So how do we decide what makes a mineral? A mineral is a naturally occurring homogeneous solid with a definite but not generally fixed chemical composition and a highly ordered atomic arrangement usually formed by inorganic processes. Let's break that down a bit and look at it piece by piece. A mineral is naturally occurring. This distinguishes between substances that are formed by natural processes and those created in a laboratory or by artificial means. Note that we say natural processes. This means that it doesn't matter where a mineral forms. What is important is the process that forms it. A substance that is deliberately produced by laboratory techniques is referred to as synthetic. A homogeneous solid cannot be broken down into simpler chemical compounds. That does not mean that it cannot be broken down into smaller pieces. A piece of quartz that starts its life as part of a mountain and ends as a grain of sand on the beach is still quartz. Its atomic composition has not changed, only its size. Because a mineral is a solid, a liquid or gas can't be a mineral. You might ask, but what about water? When water is frozen, like in the crystals that make up snow, or the ice of a glacier, it is a mineral, but when water is liquid, it ceases to be a mineral. A mineral has a definite chemical composition. This means it can be expressed by a specific chemical formula. Above we see quartz expressed as SiO2 and dolomite expressed as CaMgCO3-2. Quartz contains no chemical elements other than silicon and oxygen. It has a definite formula and is therefore often referred to as a pure substance. Dolomite, on the other hand, is like many other minerals in that it does not have such a well-defined composition. Dolomite may contain significant amounts of iron and manganese in place of the magnesium. Because of these variations, the composition of dolomite, like most minerals, is said to range between certain limits. When those limits are exceeded, it becomes something else entirely. The requirement for a mineral to have a highly ordered atomic arrangement refers to the internal structural framework of atoms or ions arranged in a geometric pattern. This geometric arrangement of atoms forms a crystalline solid. In other words, the shape of the atomic structure is reflected in the shape of the crystal. The requirement of highly ordered atomic arrangement means that minerals are crystalline. Crystals form in many different shapes, from the six-sided points of the quartz crystal shown here to cubes and even the long slender needles of naturalite. Solids such as glass that lack an ordered atomic arrangement are referred to as amorphous and are not strictly mineral. Many natural solids are amorphous. One excellent example is volcanic glass. Here we see a piece of mahogany obsidian, which is made up primarily of SiO2, just like quartz. The different colors in the obsidian are from different elements in the composition of the fluid from which the obsidian formed. These trace elements vary widely. Minerals are formed by inorganic processes, usually. I say usually because modern mineralogy accepts organically produced compounds that meet all the other requirements of a mineral. An excellent example of this is the shell of an oyster and the pearl formed within it. They are composed primarily of aragonite, identical to the inorganically formed mineral. Other examples include calcium carbonate of mollusk shells. The human body produces minerals. Apatite is a major component of bones and teeth. Petroleum and coal are not considered minerals. They are naturally formed, but have neither a definite chemical composition nor an ordered atomic arrangement. However, when a coal bed is subjected to extremely high temperatures, volatile hydrocarbons are driven off, and the remaining carbon is crystallized. This new crystallized carbon is the mineral graphite. So we see that the formation of a mineral crystal requires many conditions to be met in a very specific order. Any variation causes a change in the mineral, or whether the mineral forms at all. I hope you found this video helpful. Thanks for watching, and be sure to check out the other videos. Come back often for new content.